All right. So Sanjeev Sivarul Rasa is a man who combines both artistic and scientific perspectives. And he's going to do that for us tonight. Let me read you something from the website that introduced his solo art show, Starfields, in 2018, which featured his photographs of the stars. Sanjeev Sivarul Rasa is inspired by the night sky. He sees starry skies far from city lights as a meditative space for introspection and creativity. You can see time in the sky, he says. In the city, he said, we've stopped looking up at night. We've forgotten. Through his travels and his work, he hopes to recover an elusive serenity, a reconnection with the natural world. As his fascination with the night sky grew, he left his background in law. He has 2 law degrees to pursue art as a professional artist, a curator, and founder of the Sivarul Rasa Gallery in Almont, now representing artists from across Canada. Indeed, what first brought Sanjeev to Almont was the light pollution bylaw in the town of Mississippi Mills, which has kept the night sky reasonably dark in the Almont area. He was born in Sri Lanka, and he holds a bachelor's degree from the Arts and Science program at McMaster University. So it seems to have combined arts and science way back in your undergraduate degree, Sanjeev. You also have a law degree from Osgoode Hall Law School and a Master of Law degree from the University of Ottawa. A former member of the Royal Astronomical Society of Canada, he was named Observer of the Year by the Ottawa Centre chapter of that in 2010. His artistic photographs of stars and starscapes have been featured in several shows, and I think we're going to see some of them tonight. Over to you, Sanjeev.
Well, thank you, Carrie, for a very kind introduction. Yeah, I first started coming out to Almont to use the Fred Losing Observatory, which is on Benny's Corners Road. Some of you may know it. The telescopes there were kind of ancient, so I used to bring my own equipment and set up in the parking area because it was surrounded by a ring of trees, and it was reasonably dark. That's how I got to know Almont long before I set up the gallery here. So today I'll be talking about some of the places I've been to for dark sky observing, but also really looking at the night sky and how we see celestial phenomena and how that story has been told over the last 30 years, and how I've tried to change it with my art, and help people to sort of rethink how we see the night sky, how we see the celestial sphere in general. So I'm just going to share my screen and I'll start my presentation. Can everyone hear me okay? All right. So are you seeing my screen? Okay.
Yes, seeing it perfectly. I had to unmute myself. So
this photo is a daytime photo from Lake Superior, north side of Lake Superior. So it's from Pakistan National Park. It's about a 13-hour drive from Ottawa, almost going towards Thunder Bay. It's near Marathon, Ontario. So I like getting away to, I've been to this location twice now, in 2020 and 2022, I believe. And it's nice to get away. And these are usually solo trips, so I'm just on my own driving. And as Carrie said, it's about trying to reconnect with, a serene environment, which also happens to be super dark at night. So we'll get back to that later, but let me just. Okay, so let's start with this image. This is the Orion Nebula image by the Hubble Space Telescope. And this image is from 2006. And this image is Orion Nebula imaged by me from here in Almont. So in 2011. And this image here was done by a telescope in outer space with a mirror that's 2.4 meters wide. This one was done right here in Almont with a telescope that has a lens that's 5.5 inches wide. So when you look at these pictures, I think an important question to ask is it the power of the telescope that's creating what looks like a really beautiful picture? Because if it's the power of the telescope, I must not be able to create an image that rivals the image of the Hubble in beauty, right? You would think. So I think it's because both of these images are very, very high in emotive content. And that's because both of these images really are art. They're not science images. And art comes from the artist, comes from the vision of the artist. Art is not something that you can really separate ever from the artist. So it all depends on what language we use to describe these images and what lens we use when we talk about how the celestial sphere is being visualized. So we'll talk a bit more about this image as we go on, but basically, this is about 3 hours, 15 minutes of exposure through a CCD camera and a refractor telescope. And there's 80 separate exposures went into making this picture. And I'll talk more about how I made this image later on in the talk. So here are some of the equipment that I've used. And you know, I think with photography in general, photographers tend to get really wrapped up in their equipment. That's something that I try to avoid. So this is the only picture I have of equipment to show you. Because I really believe, if you look at it from the perspective of an artist, you're really the master of your tools. So the tools are there to serve whatever vision you have. And I don't think the tools make the art. I think it's the artist that makes the art. So I've used a variety of lenses and also telescopes, which really serve as long telephoto lenses. And then what you're seeing, can you see my cursor? Okay. This is an equatorial mount. One of the things that makes deep sky imaging challenging, I'm still getting over a cough, so I'm kind of having to pause a little bit, is that you have to track the motion of the sky. So your camera, so there's 3 cameras here. These are like DSLR cameras. One of them is filter modified. One of them is a pretty regular camera. And this one here is a CCD camera. And I actually brought it with me so I can show it to you. You know, maybe in the discussion section, I'll show you the camera itself. This camera here, the CCD camera, is what's on the back end of this telescope here. Okay. Basically, light is coming through here and is serving as a long telephoto lens. But usually you have to do multiple minutes of exposures so that you're not just doing a snapshot, because if you do a snapshot, you know, of a fraction of a second, like we do in daytime photography, you'll get just black. There's so little light in the night sky that you won't see anything. But if you do, you know, a 6-minute or 10-minute exposure, you're going to capture at least some faint light. So this CCD camera allows you to do that. You can keep the shutter open. You have to control it with a laptop. And basically, while you're doing that, of course, the Earth is turning. So you're going to have the stars trailing. You won't have round stars. Everything will be out of focus because the image will just shift. So you have to be able to track the sky accurately, meaning that your camera has to move in sync with the motion of the sky. So it takes a couple hours to set all this up. And this is at a dark sky site about 2 hours west of here, north of Wanaka Provincial Park. It's an abandoned airstrip, actually. So you first set up the mount, and then you have to polar align the mount. So through this top part of the mount here, you look from behind the mount, you can actually sight Polaris, which is the North Star. And there's actually a reticle inside here that you can use to the North Celestial Pole is close to where Polaris is, but you can precisely align your mount to the North Celestial Pole, and then now your mount is going to rotate. Inside the mount are gears, and your mount can rotate in sync with the rotation of the Earth. So you have to first polar align your telescope and then have it all rotate through the night while you're imaging. And then these are battery packs. So I'm a miser with power when I'm traveling because I don't use that much power so that I can stay out multiple nights. And all of this stuff is super portable. And the reason for doing this, because you'll see most photography that's sort of science-based photography of the night sky, a lot of people like who do in astronomy clubs, for example, will actually build an observatory if they can afford the cost, and they'll build it in their backyard or some remote location, and then have everything set up. Because there's so many things that have to be calibrated that have to work together, that if you try to build your system up from the ground up, every time you're out to image, you're more likely to forget something, and you're more likely to have screw-ups. So people tend to just set up an observatory, and then they can sit in their warm house, and they can image, remotely control their telescope. But for me, as an artist, I don't think that will work for me at all, because basically you're mediating all of your experience of the night sky or of nature through a screen. And you're kind of removing your own agency as a human being. And you're kind of, even the story you tell is the story of automation, or the story of your equipment kind of capturing these images that are out there in outer space, as opposed to how an artist would think about it. So for me, it's really important to have a portable setup that I could take with me and go to locations that I have frequented, so that I'm actually familiar with the place that I'm going to. So that's for the equipment. Now let's look at some pictures, and then we'll get into this discussion. So here's one of the most famous Hubble images. This is part of the Eagle Nebula, and this is called the Pillars of Creation. And this was one of the first images that the Hubble team released, that NASA released in 1995, and it caused a sensation. And it's a very evocative picture. So now I'm going to show you, on the right here is one of the raw images that Hubble actually captured. And on the left is the final image that NASA released. So they actually used 32 images, raw images, and to create this picture. And on the left, if you look at the top here, the middle section here that I'm pointing to, the triangle shape, that's where this picture went. The raw image went. So the thing is, when you're imaging in daytime photography, I don't want to get too technical, but I think I'll explain some basic concepts. When you're imaging in daytime photography, basically, like for example, if I were to take a picture of Carrie and her face looks red in the picture, she's going to say, "Oh, Sanjeev, that doesn't look like the right skin tone for me." And it's because, well, if I take a picture of a tree and the leaves look blue, you're going to be like, "Well, that doesn't really look like, it looks like your color is off." And it's because in daytime conditions, we actually have a mental reference point for what we see in the world. We have a reference point for what people should look like and what objects should look like. But in the night sky, we actually don't have a reference point. And partly that's because most people don't spend their time looking up at the stars or at galaxies and nebulae, and the ones that even do have telescopes are losing the sky because of light pollution. So in a sense, we only have one window to look through to see what celestial phenomena look like, and that window is through the window of science as told by organizations like NASA. So we don't have a reference point to sort of challenge what we're seeing and judge for ourselves, unless you spend a lot of time actually looking at these phenomena for yourself through a telescope with eyepieces, going to dark skies, which is what I did a fair bit of for about 10 years. I haven't had much time to do my own work in the last few years, but I did a fair bit of doing. A lot of the images I'm going to show you are from a few years ago. So this is another one, another Hubble image. This is not released about 10 years later, and it's done with a similar technique as the Pillars of Creation, but the NASA team got much better at making the colors even more gorgeous to look at. And this color scheme actually uses what's called complementary colors by artists, which is if you could juxtapose blue and orange, or red and green, these are complementary colors, and it creates a very strong emotional response. And this is part of the Carina Nebula. So let's go back to my Orion Nebula for a second. On the left, you're seeing a picture, a 90-second single exposure of the Orion Nebula. So even if you take a film camera and you expose through a telescope, you take an old film camera and you just open the shutter for a minute or two, you're going to get a lot of red, because the Orion Nebula, most of these star-forming regions emit light in the high, like there's a hydrogen spectrum, H alpha light. There's a lot of it is actually in the red part of the spectrum. A lot of these nebulae are emitting light in the red part of the spectrum. So even though it's faint for our eye, the film camera will pick up the red. But when you look at it through a telescope, you can actually see a lot of this nebulosity up on the top here with your eyes, but it looks like a greenish gray color. And it's very beautiful to look at, but you don't see all of this detail that you're seeing on the right, which is my other image that I showed you earlier. So what I would say about the picture on the left is, yeah, even with the film camera, you'll pick up that red, but you're not actually going to see the red with your eyes. So because film is a different it's a different thing than our eyes. Our eyes have a particular kind of response to light than a CCD camera would, or than film would. But if you look at DSLR cameras, like the regular cameras that we use, or the cameras on our phones, they're actually calibrated so that the manufacturer wants those cameras to reproduce what we see in natural light, in daylight. So all of those cameras have what's called, like digital SLR cameras have what's called a Bayer array on top of the sensor. So what happens is all of those cameras are all capturing light in grayscale. Okay, meaning like the pixels in the sensor are actually capturing light, the intensity of light, as a grayscale image. So it look black and white when the image is first created. But what happens in a digital SLR camera, for example, is the Bayer array is a set of filters that are overlaid on top of the pixels of the sensor. And for every 4 pixels, there's 2 green filters, 1 red filter, and 1 blue filter. So, and the reason they do it that way is because in daylight conditions, our eyes are a lot more sensitive to green light. So the ratio is really 1 to 2 to 1, red, green, blue. And when you look at the viewfinder of your camera, after you've snapped a picture, it's going to show you on your screen, it's going to show you an RGB image, which is a full color image in photography. And that RGB image has been created inside the camera because the camera knows what light went through the green filters versus the blue filters versus the red filters. Okay. So that's because the camera manufacturers want people to be able to recreate photos that look like the real world, right? So let me just go back here for a second. I think I should stop and just show you this camera here. This is my CCD camera, and whereas these are look like regular cameras. So, can everybody see this? Okay, so this is the camera. I'm going to open this. Doesn't have any kind of a screen. You have to use a laptop to control it. And there's a cooling system inside this camera. It's because in deep sky imaging, when you open your shutter and you gather light on the sensor, what's happening is the photons of light land on your chip, and each pixel is counting how many photons it receives, and it turns it into an electrical signal. And that's how, and based on the readout from each of those pixels is how a digital image is created. And it's a grayscale image that shows the intensity of the light striking each pixel, okay? So when you go to take a photo with this kind of a camera, a couple of things. One is the heat in the circuitry of the camera itself will generate noise. It'll also get counted. So you have a cooling mechanism in this camera that can bring the camera down to minus 20 degrees Celsius. So that's one of the key things about why it's so much more effective for deep sky imaging to use a CCD camera than use a regular DSLR camera. The other advantage is you actually, I'm going to open the camera here. This part is threads here. This is what goes onto the back of the telescope. Now, what you're seeing, it looks very shiny. Can you see that the shiny circular thing? That's actually a filter. So what's happening here is the sensor is right behind that filter. But what the filter is in a filter wheel. There's actually a wheel inside this body where I've got 5 different filters. Okay, the red, green, blue, luminance, and H alpha. There's 5 filters in this camera right now. And with the laptop, you can actually rotate the filter wheel so that different filters go in front of the sensor while the camera is mounted onto the telescope. So I can take like a 5-minute exposure of a nebula with the green filter, take a 5-minute exposure with the blue filter, then go to the red filter and create. And basically, I've got now 3 different grayscale images, just like the DSLR does, right? But now I can go on my computer and using software, I can tell the computer that this is red light, green light, blue light, and can you combine it? And it's going to combine it and give me an RGB image. Okay. So it actually allows you to collect a lot more light because remember, light, there's not much signal in the deep sky. It's actually pretty faint. So you want to get as much of it as you can. But if you're using a DSLR, only 25% of your pixels are going to be picking up blue light because only 25% of the pixel have a blue filter in front of them. Right? All those blue filters will reflect back light that's not blue. So with the regular camera, with every exposure, you're only collecting light that you want through some of the pixels. Whereas in the CCD camera, you're actually given more control. Each time you go to do an exposure, you can decide what filter to put in front of it and collect that kind of light. But it also gives you a lot of artistic freedom in terms of how you mix those colors together. So in this image, what NASA did is they didn't actually have red, green, and blue light. This is called narrowband imaging. And what they did is they actually used 3 very specialized filters. One is called hydrogen alpha, which collects light. And I actually have a filter just like that in the camera that I just showed you. It collects light, a very narrow band at about 656 nanometers. So if you look at the visible spectrum, it goes from about 400 nanometers to about 700 nanometers. And that's the part of the light that we see. And blue light tends to be between about 400 and 500 nanometers. Green light between about 500 and 600. And red light between about 600 and 700. So H alpha light is actually a very specific bandwidth of light that's in the red part of the spectrum. The second kind of filter that Hubble guys used is called sulfur 2, which is also happening in these near-emission nebulae, but much less than the H alpha. And that's a deeper red. It's like around 672 nanometers. And the third filter they used is called oxygen 3, which is also not as dominant as H alpha in these kinds of celestial objects, but it collects a kind of blue-green light, like a cyan light. So with those 3, if you were to combine them together, you would not get this kind of a color scheme. You would actually get a very red picture because you have 2 shades of red and you have 1 shade of cyan. You put those 3 together, you're not going to get a very pleasing image. So what they did instead is they came up with a special, what used to be called a false color palette, but they don't call that anymore. Now then they started calling it a Hubble palette. But basically what they did is they took the most dominant emission, which is the H alpha, and it's a red color. They mapped it into the green. Then they took the sulfur 2, mapped it into the red, and they took the oxygen 3 and mapped it into the blue. And by doing that, it produced this really beautiful color scheme, which actually is quite reminiscent of Van Gogh's color scheme in the Starry Night. You see a lot of blues and yellows, right? So that it creates the most aesthetically pleasing kind of color palette. But what you're doing is you're actually now playing with color, painting with light, and you're creating a work of art, right? Like the image on the right here, I think this is a scientific image, right? The one on the left is not a scientific image. It's not a science image anymore. And when NASA first started releasing these kinds of pictures on the left, people used to call them pretty pictures, and in a derisive way. But you only do that if you don't think of it as a work of art. If it's a work of art, you're going to be like, well, that's amazing. That looks incredibly evocative, even spiritual. The other problem that with this image is that when you capture light the way I said with the narrowband filters, you actually don't have enough information, enough data to create an RGB image. Because what you're doing is you just have a very tiny bandwidth of light at each of those wavelengths. But when you take a picture in daytime, you actually are collecting light across the visible spectrum. So you're collecting light from like 400 nanometers to 700 nanometers, right? You're collecting all of the colors of light, and then your camera is creating an RGB image. In this case, if you take 3 grayscale images that are from very specific bandwidths of light, and the images look like this one on the right here, you tell your computer, like you can use Photoshop, you can use astronomical software. You basically tell your computer, this is an RGB, this is blue light, this is green light, this is red light. Your computer will say, sure, and give you an RGB image. Essentially, you've created a fiction that the narrowband data you collected is actually full spectrum light. That's what you've done. So what we see on the left is a full spectrum image, and it's full of abstractions because it's not necessarily, it was not created from actually someone imaging the full red, green, and blue spectrum, right? So again, we don't have a reference point. So the question that I would ask is, what would space actually look like if you could go in a spaceship and see it? And you would think that that question would be central to a scientific inquiry. Because it shouldn't take an artist to say, well, what would it actually look like, objectively speaking? And put up your hand and ask NASA. Well, they'll tell you if you press them, they would say, well, no, it wouldn't look like that to your eye, but that's because your eye can't see, this level of detail. But I'm not sure that this is actually even detailed. I think if you go to these objects in the deep sky, they're spread out over very big distances of space, like we're talking light years across. So as you get closer, they would actually become more and more faint and diffuse. We're talking about extended objects like nebulae and galaxies. So here, 10 years later, we have an even bigger patch of sky, the Carina Nebula, and again, it looks incredible. So the question is, would it look like that if you actually go there in a spaceship? And I don't think it would. And I think that's why these are not illustrations. In science, usually we use illustrations, but in art, we don't need illustrations in art. Art is different from illustration because art exists in its own right, and it doesn't need any external validation. So if you want to take a whole bunch of data from these Hubble or James Webb, and you want to play with those colors and you want to paint with light, as an artist, nobody's going to question you because it's art. You don't need any kind of external validation if you label it as art. Okay, let me come back to this for a second. So on the right here is my image, and this, by the way, this picture actually was on the cover of Sky News magazine when I first made it. So they saw it as an astronomical image, but eventually as I started working as an artist, I wrote to the editor and I said, I don't really want to submit any pictures to you guys unless you actually label my work as art and call me an artist. So here, now I just want to talk a little bit about some of the process and just to give you a sense, because people are okay, well, so they're playing with color. Well, no, it's not just color, it's also form. So let's talk about what the structure of these objects is in space. So in science, it's called the morphology of celestial phenomena. The morphology is like the underlying structure of these things. So on the left here, you're seeing a stack of luminance. Luminance is basically a white light filter that collects light across the visible spectrum. It's red, think of it as red, green, blue. All the wavelengths of light, visible light, will come through a luminance filter. And that's what you're seeing on the left here. But because our eyes actually have more dynamic range than cameras. So this area here in the middle, with the trapezium, below the newly formed stars, I can see this with my eyes, and if I look through an eyepiece, I see those 4 stars. It's very beautiful. And actually, it kind of visually in a dark sky, you will see this top part of the Orion Nebula. You can see a lot of this nebulosity. It looks like a green-gray, like kind of like this. You won't see the nebulosity on the bottom part here. It's too faint to see with our eye, but this top part, you do see it. And it's actually one of the most beautiful sights through a telescope is to see the Orion Nebula because it's relatively close. It's 1,500 light years away. But on the image on the left, you're not seeing the trapezium because it's blown out, because it's basically overexposed, right? And you have a lot of shadow detail here. And this is typical in deep sky imaging, is that most of your pixels will be dark, will be super, super faint. So what happens, what I've done here is what's called stretching. So, and in NASA speak, this is called intensity scaling. Sometimes it's called stretching the histogram. Sometimes it's called compressing dynamic range. But all of those scientific sounding terms are really just another way of saying that you play with the brightness until you get a pleasing image. So basically, you're playing with the relative brightness that your camera captured. So your data that you captured, this is accurate. This is the data that you captured on the left. But what happens is there's a lot of detail lost in the shadow, and it's because the outer parts of the nebula are very, very faint. So, whereas the middle part of the nebula is quite bright. So relatively speaking, there's a huge range of brightness there. But now on the right-hand side, I've kind of flattened the dynamic range. I've compressed the dynamic range because I've actually brightened all of the outer areas of the image. And for the brightest parts, I've actually taken 5-second exposures, whereas on the outer parts, you have 30-second exposures, and then the rest of the darker side has like 6-minute exposures. So I've taken 3 sets of exposures with different lengths of time to allow more of the faint detail to come through. But on top of that, after I composited all those exposures together, I've still compressed the dynamic range further to basically flatten the range of brightness here so that this outer part looks similar in brightness as the rest of the nebula. And that creates what looks like a beautiful heart shape, or maybe a flower, right? So the question I have is, well, that's great. It's very beautiful and it's awe-inspiring. If I were to show the picture on the left, doesn't really pack an emotional punch the way the shape on the right does. So if I were to go in a spaceship to the Orion Nebula, would I see a heart-shaped Orion Nebula? As I get closer to it, am I going to see it? Because even on an eyepiece, I've never seen this outer part. And I don't think I would. I don't think there's any vantage point in space where the Orion Nebula would look like the shape of a heart, like the way it does in this picture. So there you go. Where does this heart-shaped Orion Nebula exist? I think it exists in the picture and in our minds. And that is a hallmark of art, because art doesn't need external validation. It just exists on its own right. And the fact that Hubble and other people who image the Orion Nebula make hundreds of subjective judgment calls to create a picture like this, it just means that they're all adopting a similar style of editing, manipulating their raw data, right? So it's like, if you look at painters, for example, you can usually discern a style that a particular artist has, and you will recognize their work. If you've seen, 5 or 10 of their paintings, and you go to another show and you see works of a number of artists together, well, you're going to be able to recognize usually the work of the artist that you saw previously. And it's because it comes quite naturally to artists, their kind of unique style, and it's an expression of who they are in some ways. But in science, our observations are supposed to be repeatable. So we're not supposed to be unique. If you saw something You need somebody to verify it and repeat that observation, or repeat the experiment and get a similar result for your observation to be valid. And because the science has a very different methodology than art. So in science, if people are creating different kinds of images of the same phenomena, well, it kind of calls into question whether those images are valid from a scientific standpoint. But so a lot of astrophotographers, when they image and make their pictures, they kind of make their visualizations look the same as NASA does. So it's actually almost like a kind of, sheep following the shepherd. So, but as an artist, I mean, I don't want to follow the shepherd. I'd like to go my own way, right? Because in art, if you copy the style of another artist, you're supposed to say, after so and so. Like you pay a tribute or an homage to the artist whose style you're imitating or emulating, and that would be the proper thing to do, to give them credit. But we don't really know who created, because these are presented as science images. I would love to credit whoever did this one, right? Because they're human beings. This is not a snapshot of outer space, and neither is this, because there are so many judgment calls that are involved in making a picture like this. Same thing with this one. So what am I getting at? I'll talk. This is my Andromeda galaxy. This was also done. I imaged this at the Fred Losing Observatory through a small telescope. And this is about 4 hours of exposures through the same camera, this camera here that I showed you guys. And actually one of these, one of the previous mayors, the late Sean McLaughlin, bought one of these, and I think it's in the municipal building. And so this is an edition of 10. Now, the Andromeda galaxy is the closest big galaxy to us. And it's beautiful. It's actually the faintest object you can see with your naked eye. It's the furthest object you can see with your naked eye. If you're under a really dark sky, it looks like a thin sliver of light. And from one corner to the other corner of the image here, it's actually about 3 degrees. In this picture, I think I have about 2.5 to 3 degrees of space. So a degree is basically twice the width of the full moon. So the sun and the moon both occupy about half a degree of sky. So if you think about degrees, you have 360 degrees in a circle. So from horizon to horizon, you have 180 degrees. This is 3 degrees of that. So it's a pretty sizable looking object. And when we talk about degrees, we're really talking about angular size, not actual size, not actual physical size, the angular size from our perception, from our perspective. So it's a pretty extended object in the sky. And these little white glowing things here, these are actually satellite galaxies, M110 and M32, which are going around M31, which is the Andromeda galaxy. So we're actually seeing 3 galaxies. And what we're seeing in front of us, what look like background stars, are actually foreground stars. These other stars are actually a curtain of stars in our own galaxy that we're looking through. So the thing about this picture as well, again, it's art, because through a telescope, I see the core. It's very, very like a ball of light. It's quite prominent. And then the spiral arms, which you can clearly tell here, are actually very, very faint in a telescope. In a telescope with your eyes, the spiral arms tend to be quite faint. So again, the way you make the spiral arms show more is that you compress the dynamic range of the image so that the relative brightness of the outer arms is increased, while the core is kept from blowing out. So basically, you're playing with what photographers would call the shadows, the midtones, and the highlights. And that's how you create a very beautiful spiral form. And it so happens that when we see spirals, whether we see hurricanes or galaxies, we're very enthralled by that for some reason, and it's really a mystery why human beings like spirals, but we do. And when you make the spiral effect more obvious, you're actually now creating an image with a lot more emotional impact, which is what artists like to do. And that is a technique of exaggerating form. Exaggerating form, whether it's the Orion Nebula or the Andromeda Galaxy, As an artist, you can do that because you want to make a picture that you know gets a response, an emotional response. But if you're doing science, I think you actually have to kind of explain yourself because you're actually manipulating the data that your telescope captured. And because telescopes by themselves don't change the brightness of the light in the universe. Only human beings can do that. And when we take the human being out of the picture, or we imply that there's no human being involved, we're denying the basic agency that people have. And by agency, I mean that we have the ability to change things, and we have the ability to make decisions, and we have something called free will, which is essential in the making of art. So here's another picture. This is now the James Webb Telescope. And the James Webb Telescope is the newest thing out there. This is one of the first pictures they released. And you can see now this, the blue and turquoise and gold motif is really reached a new level with these new images. Now, the James Webb Telescope has cameras, detectors that can detect radiation in infrared, light in infrared, or near infrared, or mid infrared. Okay, and because when you go past the red spectrum, you get into infrared light, which our eyes can't see. It's invisible to our eyes. And the thing is, there's a lot of amazing science that can be done. Same thing with Hubble. There's an amazing science that can be done with the sensors and detectors that are on these telescopes, these space telescopes. So the James Webb Space Telescope has a much better resolution than even Hubble does for doing real science, meaning you can collect data, and the data can tell scientists a lot about the chemical compositions of distant objects. It can tell them a lot about the physical structure of the universe. It can tell them all about helping the theories about how the universe formed. And these all come from very precise measurements and an understanding of where even the flaws are, like where the error is in each of the processes. It's a very precise and tedious way of doing science, of doing real science. Unfortunately, someone has made a decision that the public is not going to be patient enough or smart enough to understand the real science. Because real science is tedious and it takes many years to show results. So if you want to show the public results, and here's a $10 billion telescope, James Webb, a lot more expensive, bigger project than Hubble. Well, you put out these pictures that kind of tell a Hollywood style story. So you go from invisible light that the telescope collected to this. I mean, how did it become so visible and so beautiful? So now as you go and read a lot of the stuff you can find, if you go digging for it, you can find, articles and things where they tell you that, yeah, they're using photography principles. There's up to 27 different filters on the James Webb. So they can actually capture different parts of the infrared spectrum. And then they can decide for themselves what color to assign to each of those wavelengths of light. So you can create all kinds of, it's like giving a kid a pack of crayons. You can create all kinds of pictures. And you can also really create a lot of form with color, and also by how much you've actually played with the relative brightness of what's out there. Because what look like cliffs may actually, if you go in a spaceship, might actually not be that dramatic, because they might actually be diffused over this is the Carina Nebula, the same image that I showed you before. This is James Webb, and this is Hubble. Okay, it's part of the same nebula. And sometimes you look at image and you go, oh, this is so much sharper. Well, like there was a time when they repaired the Hubble's mirror and they released some images to show that it was so much better. Well, it could also be better because your team has now gotten better image processing skills, right? We really can't tell. unless we see the real science, we really can't tell. So this is where we are today with the James Webb. And there's a lot of stunning pictures out there, but if you go digging, you'll find that the people that really are artists, they're actually called science visuals developers. There's actually people that have this title, science visuals developers, and they're not called artists. And, before Hubble, NASA would often release artist renditions of celestial phenomena. They would have an article that scientists write, and there would be an artist rendition that shows you the scene, and you could tell that this is a visualization. Well, these are also visualizations, and even though they don't call them artist renderings, that's actually what they are. And the organization within NASA that does these images, same thing for Hubble, they're called Space Telescope Science Institute. It's basically the PR arm, and basically it's the way that NASA markets. So it's marketing, and it's not, and I think it's fine to combine art and science. I would not have a problem with it, provided it's actually called art, and provided people talk about, like with the James Webb, these science visuals developers actually talk about photography. They talk about using the principles of photography. Like they'll rotate images and they'll crop them to come up with dramatic compositions, which is what photographers do. And you have to ask yourself, well, okay, but is photography a science or is it an art form? Photography is most definitely an art form. It is not a science. So to be using photography and doing white balancing, you're doing adjustments, all these things to your image is with a view to creating something that's visually interesting. And that is what artists do. So I've talked about a number of these themes. So let's talk a bit more about like what those themes are about art and science. So, and what interests me and why I think it's really important to go out into nature and into dark skies. Because I think it's about our perception of the natural world and about everything, like really our reality. And what does it mean to be objective versus subjective? And is it a bad thing to be subjective, right? And is it ever possible to be purely objective? And what are the ways of seeking knowledge? Do we always need to defer to science? I think we need to defer to science if it's a science question, right? But if you look at the philosophy of science, we know that there's limits to the scientific method. So if it's something that can't be observed or analyzed through instruments, is it even a question for science? And I think art is different, has a different methodology than science does. And what we're seeing with the celestial sphere is we have a particular kind of visualization that's happening. And that particular style and kind of visualization, I think, to me, is a very sort of sugary kind of visualization. It's full of, it's kind of like the Marvel movies where it's all, blow them up, kind of, it's all like full of excitement, right? And what I see in the night sky and what I sense about the universe is that it actually has a lot of serenity. It actually has a lot of balance. It's a very dynamic, I think the universe is a very dynamic place. It's certainly very dynamic. But at the same time, it has balance and it has serenity. And that's what I want to bring out through my work as an artist. So I think one of the key realizations that I came to is that, because I was in the RASC, the Royal Astronomical Society of Canada, for about 10 years, and I found that people are often describing things they're very passionate about, and their passion and their emotions all through a scientific lens. And I don't think it quite fits, because in science, you're not supposed to put your emotion into your observation. Once you do that, you've tainted your observation. But if you are speaking as an artist or just as a human being that enjoys nature, you can express all kinds of things. You can color your pictures any which way you want, and nobody can question you on that because that's your work, your creativity. And there's one painter I want to reference, Vasily Kandinsky, who's a Russian painter, and he's considered one of the founders of abstract art, at least in the Western world. And he wrote a book called The Spiritual in Art. And it's a very interesting little book. And in it, he talks about, and this guy, by the way, was a lawyer before he became an artist. So he says, he talks about the artist's inner need. And he was a pioneering artist in terms of creating non-objective art. So his work was very abstract, and he was trying to kind of create a sort of a theoretical basis, I guess, for his work. But interestingly, he also points out that as an artist, your theory cannot precede your work, because your work can't just be an illustration of your theory. Like in art, your work has to lead, and then people can say whatever they want about it. And you yourself can then go and write a book about it, but you actually have to lead with your work. And what he talks about is the artist's inner need, which really comes from the soul of the artist. And in science, of course, people don't talk about their soul because science doesn't have any tools to probe that. So one of the things I've noticed is that with a lot of automation in science and in astronomy, it really is operating through a scientific lens that has become completely materialistic, meaning that the lens we're using in science now is actually the lens of materialism, which basically says everything in the universe is made of particles. And at some level, you can observe it. So even ourselves, we have a brain. And so when we have a sense of awareness of ourselves, that awareness is just a projection. Or feelings of love, for example, are just neurons firing a particular way and releasing particular chemicals in our bodies. So that in theory, you can recreate all of these procedures if you just have the right chemical compositions. Whereas if like me, you believe that materialism is only one school of thought, like if you look in the philosophy of science, materialism is one way, it's a choice. It's one way of looking at our reality, because I think it's entirely possible that there's a material realm and a non-material realm. And the non-material realm could be a spiritual realm, which is I think is where people's art, things like art comes from. And the relationship between the spiritual and the material, I think, is something that really fascinates me and interests me a lot. So I would not describe my work as coming from the telescope or from a snapshot of the sky. It's coming from me. And so this thing about presence versus automation, is a human observer necessary? I think that we've kind of, with the way that a lot of these so-called science images are created, we've kind of created a fiction for ourselves that there's no human observer, but in fact there is. And it's because you never see just the raw data being presented. You're seeing, even the way the raw data is collected involves lots and lots of choices. But once you take the raw data and create all these beautiful visualizations, you definitely have a creative mind at play, or many minds at play. And what you're doing now is actually sharing your passion for your work, which is being done in the way that an artist might paint a painting, or a writer might write poetry, because you're so moved by what you're seeing or what you're sensing. So the last point I make about this is, what is an observation? I think the observation is always the observer and the observed together, because I'm not sure that we can ever separate ourselves from the observation. We can try, certainly, to be objective. But when you look at art, I mean, in the gallery, for instance, people look at works of art, and the object of art kind of serves as a bit of a mirror, because everyone comes to it, like the artist has their own intention when they created the work. But when people come and interact with the work, it reflects back to them something of their own experience. So a person's response to a work of art is never, invalid. It's all valid because they're bringing their own experience, and the work is speaking to them about that experience. And that's why it's not really art unless it's open to interpretation. So a work of art has to remain open to interpretation, because it's never like didactic and telling people what to think, which is kind of what science does. Science is supposed to tell us things, information, facts. But when you create something that's not really an illustration, but actually is full of emotion, then it does become open to interpretation. And it becomes awe-inspiring, it becomes mysterious, which is really the kind of visualization that we're seeing when we do sort of painting with light, like the images I've been showing you. So I actually wrote a book myself about 10 years ago, and you can go on the website and find the gallery website and find it under my name. But we also have copies of it in the gallery, and this is now 11 years old. But actually, it's more like an artist statement, like a monograph, but I actually go in detail through a lot of the process that the Hubble guys do, and I critique it, and I also talk about my own process in the book. And the book is called The Vanishing Stars, Unraveling the Appropriation of Art by Science, because that's how I see it. I see it as an appropriation. And I'm quite concerned about how in the arts, like if you look at musicians, visual artists, their work is not valued in the same way that people in science and engineering are valued. And I think that this is one of the things I'm describing to you are kind of part of the problem, because we don't want to recognize the economic value of the arts. And even when we see something incredibly beautiful, we think that's science, but it's not science. It's actually art. Okay. So going out the dark skies is incredibly important because we're losing the night sky. And by going to dark skies, we're going to see, have a direct experience of nature, right? We can kind of think for ourselves. So this is a light pollution map from about 15 years ago. And all the white stuff is like, this is Montreal, this is Ottawa here, Toronto. And the green areas are kind of like Almont, would be like yellow-green. And the blue areas are pretty dark, and the black areas are the best. Up here, so where these red dots are, this is where places I've been to. Up here, this is in Western Quebec. Can you see my cursor? This is La Vérendrye Forest Reserve, and there's a very big airstrip there. It's a abandoned airstrip, and it's super dark. It's about a 3-hour drive north of Ottawa. And when I say it's a pristine sky, I mean, basically you can see down to magnitude 7. So most of the stars we see in the suburbs, like the brightest stars in the sky are mag 1 or mag 0 stars. So it's a logarithmic scale. So a magnitude 1 star is 2.5 times fainter than a magnitude 0 star. So a magnitude 7 is like the faintest that we can usually see under the best skies. So here in Almont, if your eyes are dark adapted, you can actually see down to about magnitude 6. And provided you're not near like local lights, if you're like surrounded by trees and you're like maybe 5 minutes, like the Fred Lawson Observatory, that's a mag 6 sky. And what that means is you've actually given yourself about half an hour for your eyes to dark adapt, because our pupils actually can become as wide as 7 millimeters after about half an hour of being in the dark. And if for young people, 7 millimeters, if you're older, maybe a little bit less than that. And then you start seeing a lot of detail. But if you see white light, your pupils shrink right back. This here is up here is getting into Algonquin Park. And down here is the site near Bonneco Provincial Park, which is also really, really dark. And down here, this is Lake Superior Provincial Park. This is a 10-hour drive. And Pakistan that I showed you earlier is not on this map. It's up at the top end up here. It's about 13 hours away. So the locations that I love going to that have max 7 skies are these here, like some of them are on that map I just showed you. And we're talking about a 2-hour drive all the way to about a 13-hour drive. And I think I would say that serenity and solitude equals creativity. And if you can achieve that, even if you go camping, you don't have to go look at stars, but if you're out in nature and by yourself, especially, you kind of have that chance to really become centered again, right? So I see Carrie had a question there. So they add the colors that were not in the original. Yeah,
You've answered that.
yeah, it's in the false color images definitely is added, but in the other ones like my Orion Nebula, like if you're looking at objects where the sensor can pick up certain colors, but your eye can't see it, I wouldn't say those are being added. I would say that in those cases, you're actually seeing a bit of an abstraction because the camera is a different sensor than our eye. So what would we see? What would we see, right? Unless you go out like an implant, we should let you see like the camera sensor would. Okay. So
So do
here's,
you think,
yeah,
oh,
go
you're
on.
going to show us some of the sites then. Okay, you've got more slides.
I
All right.
do. I'll go through these pretty fairly quickly. I'm just going to give you a sense of some of the pictures I've done over the years. This is one of my favorite spots. It's Acre in Grand Lake. It's about a 2 hours drive west of Ottawa. This is the same site that Tom Thompson did his paintings from, like the West Wind and um, Jack Pine were both done at this location. This is in October. It's a Milky Way in October. And this is from Lake Superior Provincial Park. And this is a place called the Old Woman Bay in 2013. And this site is a really haunting place. It's actually a few kilometers south of Wawa. It's really beautiful. And you can't camp there overnight. So you can stay late, but then you have to make your way back to your car in the parking lot. So with places like this, what I do is during the day, I would go and scope out the area. And because I have to carry my gear, so I end up trying to practice coming back to my vehicle. In this case, it was a couple hundred meters away. You have to come back. And there's actually no puddles to jump over at this place, but like no water to jump over. But if you're going out to a spot that you kind of scope out, then during the daytime, you have to know how to get back at night. And it can be a bit disorienting at night. This is also Old Woman Bay. This is more like around twilight, towards the end of twilight. This picture, soon after I started showing my work in galleries, I started inverting my pictures. And it was my way of sort of saying, hey, look, you can see the hand of the artist. This is the Veil Nebula, and this is about 8 hours of exposures. And I did the imaging here in Almont. Basically, the Veil is it's a supernova remnant. So it's an exploded star, and the circle of gas is spreading out. So all of this I did with an H alpha filter. And if I would give it a color, it would be red, but I left it as monochrome. And this part, I actually did a full RGB image and I superimposed them. Why? Because I can. See this part here? This is called the witch's broom. It kind of looks like a witch on a broomstick, vertically. This part is sometimes referred to as the waterfall. Okay, here's another picture. This is the transit of Venus, which I find really interesting. This happened only twice a century. That's the sun. And this is 33 minutes later. But I inverted the second image because it creates sort of a yin yang. So the transit of Venus happens twice every century, and they're usually 8 years apart. So that little black dot is Venus entering the disk of the sun, like it's called ingress. So basically, we're seeing a distant eclipse, right? And 33 minutes later, it's moved further up. And when I was taking this image, and this is actually one of my favorite, I wanted, it says it's a diptych, it's a two-part work, and I wanted to think about the meaning of night and the meaning of day. So the day basically means we're facing our sun, right? So I took this image at Sandbanks. There was Lake Ontario, and the sun was kind of not quite setting, but it was lowering the sky. And we could see this transit, and then the clouds came about an hour later. So it was a multi-hour transit, but I got to see part of it, and I realized that okay, I'm actually seeing the night side of Venus because from where I'm standing, right? Like Venus, I'm looking at the dark side of Venus. So I called it night on Venus, even though it was full daylight for me, right? Here's an image of star fields in Lyra. Lyra is a part of the sky where the stars are sort of not too dense and not too sparse. And I did this for 2012. Actually, the city of Ottawa bought one of these, so it's in their collection. But then what I really want to do was do a big star field. So I made this one 3 years later, and this one is in Lyra, but it's a much, much bigger area of sky. And to do this, I had to do a 16 frame panorama. I had to shoot 16 sets of images, overlap them, and then stitch them together. And then that's the star Vega, this star here. And this is, you can see this even in the suburbs. This is the constellation asterism for Lyra. And this is an accurate star field. And I wanted to kind of bring indoors a sense of the panoramic feel of the night sky. So this is how it looks. All my work is printed on sheets of aluminum. So this is what it looks like. It's a triptych. And it's about 10 feet wide. So you can do a single, shot or set of shots for this kind of thing, but you won't have the resolution. So that's why it's a panorama of 16 images. So it's actually quite difficult to shoot this kind of thing because what happens is you could be, because your lens, this is through with a small to medium telephoto lens, your lens contracts through the night as the temperatures drop. And you also have to have things like dew strips to avoid dew from settling on your lens. So your lens is being slightly warmed up through the night, but your focus is going to shift as the lens cools. So, a few hours later when you're down here, your stars should become fatter. So you have to kind of go and it's all manual focus on these lenses. You have to go and manually adjust it. Okay, and I want to show you a few visual observations as well. So, and I think I'm almost at the end of my slides. So this is part of the sky in Virgo. And I think this is 2007 when I did these. This is from near a farmer's field near Arnprior, where the skies actually were quite dark, about maybe max 6.5. And in Virgo, there's a whole bunch of galaxies. So this is my image of Virgo. And this I did over, I think, 2 nights. And it was this group of galaxies here. This is called Markarian's chain. This is M87. This is the gravitational center of the Virgo cluster. So it turns out galaxies tend to be clustered in space. So our galaxy, the Milky Way, is part of what's called a local group of about 18 galaxies. And the local group is kind of on the outskirts, the periphery of this bigger cluster, supercluster of galaxies called the Virgo supercluster. And the Virgo cluster has about 2,000 galaxies in it. So these are called elliptical galaxies. These are sort of the bigger ones, and this is considered the gravitational center. So in the spring, in May, these come up they're in the constellation Virgo. So you can actually see, even with a small telescope, they look like little puffballs. So I went out and I was lucky enough to get 4 clear nights in May of 2007. And I went out with a telescope and I actually started sketching them with these drawing little circles. And I think I observed maybe about 50 or 60 of them. And here, this is one of those sketches. You can sort of see, I've rotated the sketch. You can see, this looks like a face. You see that? This is called Markarian's chain. It's considered one of the wonders of the night sky because you can actually see a chain of galaxies. So you can actually, with a portable telescope, you can actually become aware of some of the large scale structure of the universe. If you wanted even just as to understand from a scientific standpoint, but you could also make art with it. Here's a couple of paintings. So these are studies that I did with paint, and around 2014. And I never really continued this, but to really become good at any medium in art, I think you have to work at it for about 10 years. But I started experimenting with paints, and I never really continued that. But Rigel is one of the most luminous stars in the galaxy, it's in Orion. And one thing that I love doing is putting stars out of focus, and you get these diffraction rings showing up in your telescope. And it's actually a double star. You see this little star is the companion star of Rigel. And in a small telescope, it'll split into two. So Rigel is like a bluish star. Always feels very cool to me. But actually, it's one of the hottest stars. Blue stars are hotter than orange stars. And Antares is also a huge star. It's about 500 light years away. And it's in Scorpio. And Antares, when I look at it out of focus, it feels hot to me. So this one, these are actually both paintings on aluminum. But again, this is kind of about expressing a kind of, and having an emotional response to what these stars feel like through a telescope. So in terms of my trajectory, I had shows at the Cube Gallery in Ottawa, and I got a show with the city of Ottawa. This is at the Kosh Masson Gallery, when it used to be in the market. It was on 2 floors. And that was one of the biggest solo shows I've done. And then I opened my own space in 2014, and mostly with my own work, and I started representing other artists as well. And then now, of course, there's only one of my pieces in the gallery. There's 30 other artists that are represented by the gallery, and we now have a gallery manager, and we have a professional team so that I don't have to run the day-to-day operations of the gallery. So it's been, a step-by-step process of trying to promote art and create a platform where artists can shine with their work. And that's really what the gallery is now. And my current work, I'm going to be going back to Pakistan, and this is one of the beaches in Pakistan. It's quite pristine. And this is on an image from Pakistan. That's my last slide. But my current work, I would say it's kind of still formulating in my head, and I feel like it's a 20-year project. So I've given myself lots of time, and I would like to create imagery, like express it through visual art, but really going to conceptually look at the mythologies about the night sky that people have had throughout the ages. And there's lots of that, right? There's a lot of storytelling, because people could actually see quite a bit in the night sky. Now we can't see very much. But if it weren't for light pollution, if you had a Max 7 sky, you would see so many patterns changing nightly in the sky. And you would, certainly by seasons, you would see things changing. Right? People came up with lots of stories about the planets, like the sun, moon, and the 5 visible naked eye planets. We came up with all these stories about these wanderers because they could see them moving through the night sky, through the sky against the background stars. And then across seasons, that's why that quote earlier that Carrie said, you can see time in the sky. Like Orion Nebula, one of the best times. Orion is considered like a winter constellation, but one of the best times to see Orion is like in August and September, but at 3 or 4 in the morning. And there's no bugs. And if you had these pristine sights, and 3 or 4 in the morning, Orion's coming up. And when the Orion belt comes up across the eastern horizon, it looks vertical. It doesn't look like a horizontal belt at all, because it's how it rises. So if you're seeing the Orion rising in the east, at 4 a.m., and you're in Canada at our latitude, it's most likely August or September. And so people could see all these things in the sky, all these patterns. And of course, they started wondering if there was any kind of relationship with events happening on Earth. And they came up with all kinds of stories and mythologies. And I think that's a lot of fodder there for art making. And I'd like to go to these pristine locations and somehow combine the idea of place with that work.
That sounds wonderful.
So I only saw
So,
one question in the chat. So if you guys feel free to ask me
yeah,
whatever.
unmute yourself. If you would like to ask a question, you can put your hand up and I'll call people if there's more than one person waving their hand. If not, you can just unmute yourself and say something. Okay, Margaret.
Yes. Yeah. Well, I wanted to say I agree with you on the 20-year project because I spent for over 20 years, we spent 10 days every year driving to Thunder Bay up the North Shore. So I loved all those beautiful pictures of places we've seen along the way. The Old Woman Bay, Pancake Bay, Pockesaw is one of my favorite memories. But of course, we weren't going with the idea to observe at night, but I do remember how dark it was. Um, but I still don't feel I've seen, I feel like I've seen just part of the North Shore, even though I went every year for over 20 years. I had a specific question about the North Frontenac Dark Sky Preserve, whether you had ever been there and what magnitude of star we could expect to see there.
Is that the one on Highway 41? The north is, I think
It's
it's
on it's off 41 on 506 or 509. So it's not as
what?
far as Bon Echo, like you would get to it by going past McDonald's Corners and Snow Road and Ompa and Plevna. It's near
Yeah,
Plevna.
yeah. That was the one thing in Plevna. I've been to that one too. So I've been to both of
Yeah,
those. Plevna is actually the Plevna one is quite dark. It's not probably not on a Mag 7 from. I haven't been there in the last 7 or 8 years. And
yeah.
when I went there, there was an immediate problem with it, which I think they've fixed now, which is that it's located right next to a helipad, and the helipad has
Oh,
all these green lights. And
yeah,
and as your eyes become dark adapted, these lights look incredibly bright, and they couldn't turn them off because there could be emergency landings. Of, of
right.
and so I don't know how that was resolved, but um, I did go there just once, but I didn't go back because of the helipad lights but it is the skies there are probably like not quite Mag 7, but probably like a 6.5 or better.
Yeah,
And then that Plebno one is only 1 hour and a half, 1 hour and a bit from here, I think, but from Almont. But the one that I was really interested in was the one Highway 41 because it's actually just, I think it's just south of Caladar, and it's maybe about a half an hour drive from the airstrip that I go to at Irving Lake, which the airstrip that I go to is it's surrounded by all these trees, and it's a very flat panoramic horizon that you have. And people from stargazers from Ottawa, Toronto all go there and they actually nicknamed that site Nirvana. But you actually have to drive a couple of kilometers into the bush to get to it. So some people don't like doing that. So that's why I think it's actually better. But the problem with the one on Highway 41, I only went to it, I think I've been to it twice. It's a really beautiful platform, but it's built very close to the highway. So once your eyes are
it's
dark
true.
adapted, you actually there's these trees in between, but when trucks pass by on Highway 41, they light the trees opposite, right, in both directions. And there's a lot of trucks on Highway 41. So you kind of have to shield your eyes every time you hear a truck.
Yeah, I guess that's the secret really is you probably have to go away from the highway and into the bush to get
Yeah.
away to really
And
get away from the
and the other thing is
lights.
it became really popular. So basically there's a lot of guys that would go there, most of them were guys with their camera
Yeah,
screens and their laptops, and there's no shielding because a lot of people that approach the sky through a scientific lens, even the amateurs, they don't really care to put their eye to an eyepiece, so they don't care about the dark adaptation. So there's a lot of white light at these places. If there's a few observers there, there's too much white light. And even if you're
yeah,
using red light, so I use red light. Red light maintains your dark adaptation, but it has to be very dim red light. If you have a really bright red light, It's still good. And if you look at white light when your eyes are dark adapted, your eyes will actually hurt. Because all of a sudden you're going from having your pupils like dilated to going like this.
I'm just going to turn off the recording, and then we do have a couple more questions, people with their hands up. So let's move to Helen next. Just a second, you'll hear that.